Hi everyone. So far in the series of lectures on the transient analysis of integrators and differentiators, we have discussed step response of non-inverting and inverting integrators, both RC and RL, non-inverting and inverting differentiators. Now I thought it's the right point to talk about the step response of ideal differentiators. Though differentiator circuits are not very commonly used because we saw the problems with the differentiator circuits, they are not very commonly used. From an analysis point of view, these are some of the most interesting circuits. Okay, so I thought I'll take a very interesting example of an ideal RC differentiator and show you guys all the interesting phenomenon that takes place in it. Okay, so the circuit that we are going to analyze is a very simple ideal RC differentiator. The op amp is assumed to be ideal. It's given that the DC gain of the op amp is 100 decibel, which means it is 10 power 5 volts per volt, which is a really large number. For most of the analysis, we'll assume that it is ideal. And it's given that the saturation voltage is plus minus 10 volts. And the RC time constant is given to be 1 microsecond. The input to this differentiator is a pulse input. Okay, which a pulse input is nothing but, you can see at t equal to 0, you can treat it like a positive step input. A step input of 10 volt is applied to it, and then at t equal to 1 millisecond, you can treat it like a negative step input. Okay, so we'll first analyze what happens to the circuit at the positive step input. So if you see, 1 millisecond is a really large duration compared to the differentiator's time constant, which is just 1 microsecond. So for all practical purposes, you can treat this, the positive step input, as an actual step. Okay, and then analyze the circuit, and then we'll see it's very easy. Once you analyze what happens to the circuit for a positive step, we can very easily analyze what happens at the negative step as well. So first, in this lecture, we'll analyze the positive step. So again, the usual way, first we'll find out what happens at t less than 0. So which is, I'm interested in finding out what is the value at t equal to 0 minus. I'll assume that the capacitor voltage is 0 initially. So if the capacitor voltage is 0 initially, the voltage across the capacitor is 0 initially, since we are going to assume the circuit has been in the steady state for a very long time, the capacitor will act like an open circuit. So no current is flowing through the cap, which means no current is flowing through the resistor as well, right? The input current through the op amp is 0, so no current through the resistor. So now if you see this part of the circuit, it just looks like a voltage follower where the non-inverting terminal voltage is 0 volts. So output will also follow this, output will come to 0, and this node voltage will also come to 0 volts. So V of 0 minus is precisely defined, and so here it doesn't depend upon the cap's initial voltages, so it will be exactly equal to 0. Okay, so now we know the circuit's output is going to start at 0 initially, and we see what happens now the step is arrived. Suddenly at t equal to 0, a step of 10 volts appears at the input of this differentiator. What will happen? Your capacitor will act like a short circuit. Because your capacitor acts like a short circuit, the inverting terminal voltage will also come to 10 volts. Okay, so this is what will happen. Your capacitor will act like a short circuit, and the inverting terminal voltage will be forced to be equal to 10 volts. So your capacitor's impedance will become 0, right? It's like a sudden step input. I told you guys, you can treat it like a sinusoid of infinite frequency. At that instant, at t equal to 0, this will look like a sinusoid of infinite frequency to the circuit. And what's the impedance of a capacitor for an infinite frequency sinusoid? 0. So it will act like a short circuit. So the 10 volts will appear as it is at the negative terminal. Okay, it directly follows from the fact that capacitor's voltage cannot change instantaneously. I mean, when I say capacitive incremental impedance is 0, it all translates to that. It's a different way of saying the same thing, right? If I say the incremental impedance of a cap is 0, it just means that the voltage across it cannot change instantaneously. It simply means that even if I'm injecting a finite current, the I times the impedance product will be 0, so which means incremental change in the voltage across the cap will be 0. So leaving that aside, the voltage at the inverting terminal will be equal to 10 volts. So Vx of 0 plus will be equal to 10 volts. So now if you see, right, we are forcing the inverting terminal's voltage. Generally in op-amp circuits, usually it's the output terminal, the negative feedback voltage from the output terminal will decide what Vx will be. But now since we are forcing it, driving it using a voltage source here, there is no negative feedback in the circuit, right? There is no negative feedback. You can quickly see that the feedback factor is 0. Even though op-amp has a high forward path gain, its feedback path is 0. So therefore, I can assume that the op-amp is not a negative feedback and treat it like an open loop circuit. So your Vx is Vx of 0 plus is 10 volts. The differential input voltage appearing across the op-amp is V plus minus V minus. V plus is at 0 volts, here, minus 10. So the differential input voltage across the op-amp is minus 10 volts. So which means what happens? Your output will be immediately forced to go from 0 to minus 10. It will go to minus Vsat. In this case, it's minus V10. So this is what happens. Your output jumps from 0 volts to minus 10 volts at t equal to 0. If I remember right, this was one of the gate questions where a step input was given and you are asked to find out what will be the output voltage at 0 plus. The output voltage, depending if it's a positive step that you are applying to this differentiator, your output will go to minus Vsat. If it is a negative step that you are applying to the input voltage, your output will go to plus Vsat. Yeah. So now we know what's the value at 0 plus. What happens for t greater than 0 plus? Since we said the input is being forced, your capacitor is acting like a short circuit and the inverting terminal voltage is now forced by the input voltage, your op-amp is now out of the picture, right? Your differential voltage is 10 volts. Your op-amp's characteristics look like this. Even if you assume a very high DC gain, your op-amp's characteristic is going to look like this. And you have applied a huge negative differential voltage of minus 10 volts and the output is saturated to minus 10 volts. So in this region, the gain of the op-amp is 0. Right? The incremental gain of the op-amp is 0. So I can just remove the op-amp and treat the output voltage like a constant DC voltage source of minus 10 volts. Now you will be left with a circuit that looks like this. At the input plate, at one side of the capacitor will be at 10 volts. Step has already arrived. Now we are at t greater than 0 plus. So this node voltage will be at 10. Vx of t, the other end of the capacitor will be at 10 volts, right? This is just at 0 plus. Vx of t is at 0 volts. The other end of the resistor is at minus 10 volts. Now to see what happens to the output, we'll analyze and see what happens to the node Vx. Okay, what happens to the inverting terminal node voltage, and based on that then we can see what happens to the output signal. So how do you find the voltage Vx of t? The circuit reduces to a simple first order RC circuit. And we know whenever there is a first order RC circuit, if you want to find any node voltage, you need to know what is its final value, what is its initial value, and the time constant. The time constant in the circuit is simply RC, which is 1 microsecond. And the initial value of Vx of t, Vx of 0 is 10 volts. It starts off at 10 volts shown here. And the final value, when is the steady state achieved in the circuit? The steady state is achieved when the capacitor will act like an open circuit or when the current in the circuit goes to 0. So whenever you have a series RC circuits, the steady state is achieved when the current in the circuit goes to 0, right? Your cap will act like an open circuit. When the cap acts like an open circuit, the current through the resistor will also be 0, which means if one end of the resistor is at minus 10, the other end should also come to minus 10. So Vx of t has to come to minus 10 in the steady state. So Vx of infinity, the final value of Vx is minus 10. So you know the initial value, you know the final value, you know the time constant, you can draw the waveform now. So this is how Vx of t will look like. At t equal to 0, it was 0, suddenly it jumped to t equal to 0 plus, it is at 10 volts. And it is now going to go through a discharge, an RC, first order RC discharge with a time constant of 1 microsecond. and it's going to discharge to, finally it's going to reach, it's trying to reach minus 10 volts. Now as this node voltage Vx of t is decreasing, if you observe Vd of t, the differential input to the op amp, that is always less than 0. Okay, as it is decreasing, it is at minus 10, so op amp is properly in saturation region. The DC gain is, the incremental gain is 0. So it's not the output, there is no incentive for the output to change. Output will stay put at minus 10 volts. So output will stay, output here, initially it was at 0, it jumped to minus 10 volts, and it is going to stay at minus 10 volts because your Vd, the differential input to the op amp, is negative. Your differential input to the op amp, Vd of t, is simply equal to minus of Vx of t. As long as Vx of t is positive, the op amp's differential input will be negative, so your output voltage will be at minus Vsat, which is minus 10. So now your node voltage Vx of t is decreasing, and at some point it's going to reach 0. Right? It's trying to go to minus 10, so at some point it will reach 0. The moment it reaches 0, the op amp will now be triggered, right? The op amp will now come into the high gain region. So when your Vd becomes 0, the op amp will immediately now come into the high gain region. When the op amp comes into high gain region, it will then quickly try to follow, it will act like a voltage follower circuit. Okay, then the rules of negative feedback will start applying. So I'll try to explain it intuitively first, then I'll try to convince you in a proper method, in a rigorous way. And in fact, we'll use another intuition. Very clearly you will see what will happen to the op amp's output and why will it come to 0 volts. I'll explain why it will come to 0, but why will it come to 0 volts. First, a simple intuition. As your Vx node voltage was decreasing, we said that when it started at 10 and it reaches 0, what happens to the capacitor voltage? This node voltage was initially 10, it reached 0, so the capacitor is now charged to 10 volts. Okay, so now let's assume your Vx of t is slightly decreasing less than 0. It has reached 0 just at this point, okay, and then it is trying to go to negative values. When it goes to negative values, your differential input becomes positive. So then your output voltage now will start rising from minus 10 to plus 10, because it's now trying to change to because your Vd is greater than 0, it will try to go to plus 10. Okay, so it will start rising. As your input is trying to rise, when it reaches 0, what happens to the current in the resistor? It becomes 0, because on one side it is close to 0, Vx is still close to 0, right? It's slightly become negative, but it's still close to 0. Okay, the other side is also 0, so the current through the resistor becomes 0. If the current through the resistor becomes 0, the voltage across the capacitor will also remain constant, it won't change anymore. So now the circuit has reached a perfect steady state operating point. Output comes to 0, the inverting terminal is at 0, and the current in the circuit is 0, and none of the states, when I say states, I'm referring to currents and voltages, in the circuit will change anymore, which means the circuit has reached a steady state point. So that's what happens. At t equal to, I'll call this time instant t on. So it starts off at 0, it goes to minus 10. At t equal to t on, okay, it immediately comes to 0. This is using intuitions. I was just able to explain it using intuitions. We said that's the most logical operating point it should settle down to. Okay, it tries to rise from minus 10, comes to 0 and settles at 0, because from that point onwards there is no other incentive for the circuit to change. So it has reached a steady state operating point. So this is how the output should ideally look like. And what is this time? The duration of that you can easily find out by solving this equation. You just have to, you know the initial voltage of 10. What is the time it takes for this to reach 0 volts? So I can directly use the voltage Vx of t for all time can be written as Vx of infinity, the final voltage minus the initial voltage, times 1 minus e power tau, t upon tau plus the initial voltage of Vx. What is that? So the final voltage is minus 10, initial voltage is 10, so it will be minus 20, 1 minus e power minus t upon tau plus Vx of 0 is 10. So you'll have this expression. You can equate it and find out the time t on at which it goes to this. See, if you look at this curve, right? If you look at this graph, you can intuitively guess from the graph itself. What is 0? 0 is nothing but the half value of the function. The final value is minus 10, initial value is plus 10. So 0 is the point at which it has to reach half its final value. And we can, if you guys have taken any basic course on electrical circuits, you know the time it takes for an RC circuit, first order RC circuit, to reach half its value is usually given by what? Tau ln 2. I mean, you can easily solve this equation and get that same value. If you equate this point to 0, you are interested in finding out the time at which Vx of t goes to 0. And if you equate that, you will get t on, where t equals t on, to be equal to tau ln 2. I think that comes to 6.69 or something. So 0.69 times tau, tau is 1 microsecond. So it will come to 0.693 microseconds or something. So this will be the t on, the duration of on time will be tau ln 2. That will be the on time duration for the circuit. So I just said a few moments ago that I will try to convince you why this will return to 0 using some simple intuitions as well, some little bit more rigorous analysis as well. To do that, to find that how the behavior of the circuit is going to be when your Vx of t reaches 0, what I'll do is I'll assume that the op amp has finite gain. Okay, so if the op amp has finite gain, the characteristics is going to look something like this. The op amp's gain will remain finite until your differential voltage is between minus 10 by A to plus 10 by A. If your differential input reaches plus 10 by A, output will reach 10. Any value of differential input Vd greater than 10 by A, output is saturated. Any value of differential input less than minus 10 by A, again output is saturated. In these regions, when your output is saturated in these regions, the gain is 0. So if I differentiate this graph, I will get the gain graph. If I differentiate this graph, I will get the gain. So in this region, if you see this graph, from minus 10 by A to plus 10 by A, the gain of this op amp circuit, the gain of this op amp will be A. In our example, it was 10 power 5. Right? It's 10 power 5 is what we assumed. 100 decibel was what was given to be the gain, which is 10 power 5. Now let's come back to the circuit. Now we are analyzing the circuit. To find out V0, I will try to find out a mathematical expression, mathematically see what happens to Vx of t. And then from that I will try to figure out what would have happened to V0. Right? Because Vx of t is simply what? Minus of Vd. Vd is the differential input to the op amp. It's just negative sign. So if I know what is the Vx of t, I can easily from this graph, using this graph, I can tell what should be the value of V0. Because if you see it, there is a mapping between Vd and Vd is nothing but minus Vx and V0. There is a unique mapping between, for every value of Vd, you have a precise value of V0. So if I find out Vd or Vx, I can find out V0 as well. So now let's come back to the circuit. So your Vx of t is now decreasing. It starts decreasing and it reaches a value of say 10 by A. It starts off at 10. It is now discharging. It has not come to 0 yet. It has just reached 10 by A. When this circuit, when this output node voltage reaches 10 by A, what happens to your differential input? Your differential input will be minus 10 by A. So you will be, if you look at this graph, you will be at this point. Your differential input has just reached minus 10 by A and it is further going down, right? It's slightly decreasing. Now the moment your differential input becomes less than minus 10 by A, you are in the high gain region of the op amp. You are in the very high gain region of the op amp. What happens in this region? To analyze the circuit, now I can replace the op amp with a gain of A. In this region I can replace the op amp with a finite gain. I'll just replace the op amp with a finite gain. Now I'm supposed to just analyze this circuit and find out what is this node voltage. To do that, I'll just use Miller's theorem. If I want to find this node voltage, all I need to know is find out what is the node impedance. Once I know the node impedance, then I'll see how to find out, because I know that node is going to be resistive. The impedance of the node is going to be resistive. Then I can use first order RC charging results to find what will be the voltage. So the node voltage, the node impedance, this part of this op amp and a resistor in feedback will look like a resistance of value R by 1 plus A, right? So if you have a resistor connected between two terminals of gain minus A times say Vi here, so this is Vi, then the resistance seen at the input is given by R by 1 plus A. That follows from Miller's theorem. So this circuit, I can replace it by a resistor. This op amp and resistor, I can replace it by a single resistor of value R by 1 plus A. So now you see guys, the circuit suddenly, when you reached V10 by A, when Vx reached 10 by A volts, the resistance is suddenly changing to a very small value. Until then it was what? It was just a capacitor and a resistor of value R, and there's node voltage, the other end of the resistor was at some voltage, and it was just decreasing with the time constant of RC. The moment this voltage reaches 10 by A, the node voltage Vx reaches 10 by A, the op amp starts coming into action. You are now in the high gain region of the op amp. You are in this region. I have shown here, you are now in this region. Now op amp kicks into action. What does the op amp kicking into action mean? It will now, the node voltage Vx will charge very differently. Why is that? Because the resistance seen at this node, previously since the op amp was not present, the op amp was open circuit, I could just ignore the op amp and treat the resistance seen at this node was just equal to R itself. But now that the op amp is present, the resistance seen at this node will be R by 1 plus A. Okay. Now what is the time constant of this point, after this point? So what happens? Your Vx will start off at 10 volts. It will start discharging. It will reach a value of 10 by A volts. From that moment onwards, your discharging will happen, but it will be happening at a much faster rate. What is the time constant? RC by 1 plus A. So if your RC is 1 microsecond and A is 10 power 5, I will assume 1 plus A is close to A, 10 power 5, what will this come to? It will come to 10 picoseconds, right? So I can write it as 10 into 10 power 7 or 10 in power minus 7 into 10 power minus 5, so that will be 10 picoseconds. So this, from this point onwards, from 10 by A, it will decay down, it will discharge at a rate of 10 picoseconds. It will discharge very fast at this instant. Now if you know Vx of t, what is V naught of t? Once the op amp enters the high gain region, your V naught of t has a very fixed relationship with Vx of t. V naught of t is simply equal to, V naught of t is simply equal to minus of A times Vx of t. So if you know Vx of t in the high gain region, you can calculate the V naught of t by multiplying it by minus A. So in this region, I simply have to take this waveform Vx of t and multiply it with minus A. What happens when I multiply it with minus of A? I get a waveform that looks something like this. A waveform that looks something like this. So the output voltage will come to minus 10. It will be at constant value of minus 10. At this time instant, when the node voltage Vx reaches 10 by A, it will start discharging with a much faster time constant. The time constant here is RC upon 1 plus A. Okay. So you multiply 10 by A with minus A, you get minus 10, and then it discharges from there. It will go from minus the negative voltage to 0. Here it comes from positive voltage to a 0 value. This is how the circuit will behave. Now if your A tends to infinity, what happens to this graph? This RC discharge will be like a step discharge. Discharging happens instantaneously. So that's what it will look like. So this 10 by A point goes to 0. 10 by A goes to 0 and the discharge will happen instantaneously. So it will go from 10 to 0 here, and the output voltage will also suddenly go from here to here. So this is what happens to the circuit. So if you see, it's a very interesting circuit. You fed a step input to this differentiator circuit, RC differentiator. What you got as an output? Out came a negative pulse. The duration of the pulse was given by, in this example it is tau ln 2. You will have to calculate what is the on time using the equation I showed. Find out Vx of t and find out the time at which it goes to 0. That's what you need to do. Okay. If you find the time at which it goes to 0, that will be your on time of the pulse. So it will stay at minus Vsat and then it will go back to 0. Okay. I'll do a more detailed analysis. We should, in theory, what happens when I apply a negative step, a similar thing should happen. You should expect it to get you should get some kind of a positive pulse and it will stay on for some time and go to 0. I'll talk about that in more detail in the next lecture. But in this lecture, I just wanted to talk about the positive step input. If you can digest all these points, then we'll be able to go much further. Thank you.